Okay, good morning, everyone, and welcome to the GIST Sea Level Rise seminar. We're very glad to have Pei-Chin Wu. She is a PhD student at the Graduate School of Oceanography at the University of Rhode Island, where she utilizes satellite remote sensing data to study subsidence in cities. And she's advised by Dr. Meng Mat Wei, and she's an author on several recent studies that focus on subsidence in New York City and other cities around the world. And she entered the University of Rhode Island in the fall of 2019 and earned her PS and MS from National Taiwan University. And today she will be speaking on the topic, the weight of New York City, possible contributions to subsidence from anthropogenic sources. So welcome, Pei-Chin.
Hi everyone. Thank you. And yeah, I'm Pei-Chin Wu, and I'm the second author of this paper, The Weight of New York City, Possible Subsidence Contributions from Anthropogenic Sources. So I'm the second author, and the first author, Tom Parsons, is from USGS. And in this research, our study explores how New York City is sinking, partly because of the weight and pressure of its buildings. And we use different models and compare our findings with satellite data. So about the 5 different finite element model are contributed by Tom Parson, and I'm contribute to the how to analyze the satellite image and get the inside data in New York City. So our work actually, our work not only focus on New York City, but we want to raise concerns for coastal cities throughout the world. And you can see that in the right figure, it is our satellite data in New York City, and the blue color means that the subsidence rate is higher in this kind of area. So I'm excited to share our finding with you today. So thank you for being here. And before I start to introduce our New York City resort, I would like to mention another my previous study. It is about I use satellite data to analyze 99 coastal cities throughout the world. And in this map, I use satellite image to create the maximum subsidence value I got from these 99 cities. And before, we know that subsidence is a serious problem in Southeast Asia. But in my research, I found that satellite-based results indicates that subsidence is common in cities throughout the world, not only in the Asia, but also some of the city in Europe, Africa, and the United States meet with the same problem. Because in this figure, you can see that the orange and yellow color, the orange color, and it is between 10 to 20 and 20 to 30 subsidence rates, millimeter per year subsidence rate, and it's not only in Southeast Asia. So it is a global problem. So this map is I use another method to describe my data. So it is the size of low elevation fast subsiding zone. It means that I calculate the data which is faster than 2 millimeter per year subsidence rates in the lower elevation. Lower elevation, I means that which elevation is lower than 10 meters along the coastal regions. So in the 99 cities, I pick And I found that in 23 cities, more than 100 square of kilometers of the lowlands within cities' boundaries are subsiding faster than the sea level rising. And we can see in this map, not only Southeast Asia, some of the east coastal cities in the United States also meet with the Subsidence province. So we want to pick this is why we pick one of the east coastal area and want to zoom into the New York City details and know what happened there and know why the substance is there. Yeah, so now I want to do a background introduction about the urban subsidence in New York City. So about the background, there are a lot of different research said that like global sea level rise is about 200 to 600 millimeter by 2015. And the city subsiding is 4 times rate than faster than stable region. So because we know that New York City is an iconic city in the United States, and there are 8.4 million populations in New York City. So it is a very important problem. So New York City unique challenge is because the sea level threat is 3 to 4 times than global average, and at the same time it also have another effect is post-glacial isostatic effect, and the predicted subsidence rate is about 500 to 1,500 millimeter by 2,100. And so in our satellite image in this research, we measured that subsidence by INSAR data is about the average is about 2.1. The most of city areas value is about 2.1 millimeter per year. So if like cumulates about 100 years is about 200 millimeter per year. So even now it is a small value, but if it's calculated, it will have a big impact in the future. So the third thing is major cause of subsidence in New York City. In the past, we know that groundwater withdrawal, natural compaction, and tectonic effects can cause the subsidence in the city area. But now we want to know the new factor, the weight of buildings. We know that the weight after the construction within the 1 year, they will have the primary settlements caused by the construction, and it is acceptable. But there are another thing is secondary settlements may caused by the weight of the building, and we want to highlight this part. So understanding subsidence in New York City. First, because there have 3 parts: sea level rise, subsidence, and increased storm intensity in New York City. So it is a problem we need to focus on in the future. And the second is the unexplored factor, the weight of the building in New York City. So in our research, we want to know the role of the building in subsidence, and we want to analyze. We use multi-physics finite element model to analyze. And third, because the New York City is the geological background in New York City is complicated, so we establish different kind of elements model, like clay rich soils versus elastic soils, and we want to and after we establish the model, we compare with our observe rate from satellite data and from GPS data. And actually, we don't accept that human-built environments can explain all subsidence in city area, but we want to highlight its contribution. So first, we calculate the building mass and distributed load for New York City. And the data we use is from a public database by Microsoft. And we has access we has access to the building's outlines and heights for over 1 million structure in the New York City by this Microsoft Open Database, and by estimating the number of the floors and total area, because we can get the outline and the height from this database, so we can do some assumption and calculate the number of the floor and total area. We could we can know the New York City's loading. So you might have heard that there are two different loads, which called life and dead loads. Simply, the life loads represents the contents inside the building, and the dead loads dead load means the building structure itself. So based on average values, we estimated the total mass of all buildings in New York City to it is about 1.68 trillion pounds in New York City. So it's a very very big number. And because we want to give a clear visual representation, so we separate this data. The left figure is the database from Microsoft, and the right figure is what we separate the data into over 1.8 million cells. Each cells is 100 meter by 100 meter in New York City. So, and another thing I want to mention is it is a conservative estimate. We only consider the building in New York City, but not include roads, parks, or other infrastructure. So this data then serve and so this data will as an input for our finite element model I will mention later. Okay, so for the left figure, it is the geological map in New York City. So in New York City, you can see that yellow color means artificial field, and it also have others like beach deposits, glacial lake deposits, and other things. So because New York City's geological materials not is complex, so we use different model to want to establish a model which can which is close to the real situation. And for the right figure, it is the bedrock profile in the New York City. We can see that the bedrock is from 0 to 250 meters depth. So close to the Manhattan, close to here is Manhattan, and close to the Manhattan, we can see that the bedrock is very is shorter than other place. So so in Manhattan, there are some buildings which we think it is built directly on the bedrock, and far away to the Manhattan, the building, the bedrock under the building is not as shallower as the Manhattan. So it is another thing I want to mention here. And the bedrock information are from the borehole well and the outcrop in New York City. Yeah, so in this slide, there are 5 different finite element model in our research. So from A to E, this is A, B, C, D, and E. From A to E, it means that the model is from pure clear soils to hard unfractured rock. So for the A, the value of subsidence is about 200 millimeter per year, and for the E, because it is only bedrock, so the subsidence value is lower than 5 millimeter per year. So we can know that different soil type and different soil type or soil types or rock will it is very different for it will have very different behavior. So the D model is special because in D we combine with the geological map. So in the model D we consider the geological materials, and it is closer to the real situation than other finite elements model. So in this figure, I want to show that this is the model I mentioned in the previous slide, A, B, C. And we can see that if more pure clay, the subsidence value will be higher. So in the figure A, the median subsidence value is about 294 millimeter, and for the C is about 61 millimeter. So it's very different. And not only and because this kind of data is the total subsidence values include primary settlements and secondary settlement. But actually, a lot of buildings in New York City are built like long time ago, not recently. So when we compare with our INSAR data, because INSAR data only can capture the recent 5 years subsidence value, so it doesn't have the primary settlement, so it's only can record the secondary settling in the data. So it is why from our INSAR data the value is lower, and the value is lower, but in our finite elements model the value is higher. Yeah. So but you can see that the figure in the right lower corner, within after the construction, within 1 year, within 1 year it will have the primary settlement, and after 1 year it will have a lower subsidence rate, but still have the secondary settling. So it's the secondary settlement is still significant if in the clay reach there, because it still have in 100 years it can have the 10 millimeter subsidence. So it still contributes a lot. Okay, so now in the previous part it is contribute to my our first author and Tom, and now I would like to introduce the data I analyzed from from inside satellite image. So now I would like to use this slide to briefly introduce what is INSAR and how INSAR work. So we use INSAR to monitor ground surface, ground subsidence, and the INSAR use satellite image. So when the satellite go through one target, and it will emit a signal, and in the satellite image, it will records the phase in this time. So after a time period like 12 days, when the satellite fly through the same building again, it will emit another signal. And if the targets like subsidence, the signal will the phase will be longer. So in the second satellite image, it will record a longer phase in the satellite image. So by INSAR technique, we will calculate the difference between the different phase between different satellite image. And so use a lot of different satellite image, we can establish a INSAR time series and know the time series and establish a time series about the ground subsidence. Okay, so in this research, we use Sentinel-1 radar image and to analyze the results between 2015 to 2020. It is because Sentinel-1 data is started from 2015, so we get this 5 years data for New York City. And the data I use is 6 radar image per year for 5 years. And the method I use is INSAR. It is like what I mentioned in the previous slide. We use we use software to calculate the different phase between different satellite images. So the software I use is Snap and stems and trend. So for the snap, it can calculate the different phase of different phase between different radar image. And it is a specific INSAR technique I use, which is called PS INSAR. It can capture the persistent points from the radar image. It means that it will have a better performance in the urban area, because in the urban area there are a lot of buildings, and for the buildings it will have a lot of persistent points on the outline of the building. So in a different satellite image, all image can find this kind of persistent points. So for the urban area, I choose to use PS INSAR because it can have higher resolution in the urban area, and because the satellite image only can record the phase from along the direction from the satellite to the target. So it need to have a reference point, because it only can calculate the relative deformation between satellite and surface. So I use GNSS data in the Nevada Geodetic Lab database to as a reference points in New York City. So okay, so from the INSAR results, it indicates that the subsidence value for New York City is about 1.77 millimeter per year. So the INSAR data is the left figure. So I mentioned in the first slide, the blue color means that's the faster subsidence rate, and the black outlines in the black line in the left figure, it means the artificial fields area. And we can see that some of the blue blue color are located in the artificial area. So in our INSAR data, we found that a lot of subsidence area is located on the artificial fields in New York City. So compare with our finite elements model in the middle, and we found that some of the substance may contribute by human beings' behavior, but not we cannot expect not all of the substance can explain by it. Yeah, and for the right figure, it is the data from GNSS station. So from the GNSS station, we can see that the subsidence rates captured by the GNSS station is also 1 to 2 millimeter per year in New York City. And so we think that the cause by these subsidence rates may be caused by the deglaciation, the 20th century ice and water changes, and maybe groundwater extraction, recharge, and building loss may be the factor here. And another thing I want to mention is because the bedrock in Manhattan is very is shallow, and it is made by sheets, marble, gneiss, and other things. So another thing is because the bedrock in Manhattan is shallow, so a lot of building is built on the bedrock, so it will cause lower subsidence rate than built on the sediments directly. And so from the INSAR data and our model, we think the major subsidence area associated with artificial fields. And because the rainbow color is very hard to read, so we use another map to show our data. So in the left figure, it is the data which is INSAR subsidence rates bigger than 2.75 millimeter per year, and the right figure is we use INSAR data overlap than our model with the consider with the geological material, and we can see that they are comparable. Yeah, and so okay, sorry. So about the New York City's subsidence and impact, because the New York City's population is about 8.4 million. So it means that if New York City face the subsidence problem, a lot of people will under the risk. And another thing is the Hurricane Sandy in 2012 and Ida in 2021 have highlighted the risk of the city, and however the challenge we are confronted with are not only due to natural changes, because we know natural changes is a big problem, but anthropogenic factors such as urbanization and the weight of buildings are another thing we want to highlight. Yeah, so and New York just a coastal city in the world. However, a lot of coastal city also meet this kind of problem, and in the future, I trust that we trust that more people that in coastal city the population will be higher in the future. So we need to consider the global subsidence issue with growing population in coastal cities. Yeah, and thank you. Yeah, any questions?
Thanks very much. Yes, we have a question.
Yeah, I have a question. Can you hear me?
Yeah.
My question is, I have two questions actually. What fraction or proportion of the total subsidence in New York, including GIA and groundwater withdrawal, long-term land subsidence, etc., what fraction of that is attributable to the buildings on average and also in the hotspots? And then the other question is, do you know whether building engineers or civil engineers take this type of subsidence due to the building load into consideration in their construction projects?
So for the portion, actually, we trust that most of the portion of subsidence recently are contributed by GIA, not the weight of building. But actually we are not sure the portion. We are not sure the exact number, but we trust that most parts are from GIA, not the weight of building. But if we want to double check, because the resolution of our data is 100 meter by 100 meter, so if we want to do more details about it, we need to zoom in and check about each buildings, like 100 pixels and 100 pixels higher resolution, and we can make sure the portion from the weight of New York City's building. And for the civil engineering, I trust that because before the construction of all of the construction will consider the primary settlement. Yeah, but because the secondary settlement, which is like 100 years for 10 millimeter per year, so it is very easy to not include considering. And so our research, it is in our research, it is another thing we want to highlight. Yeah, the secondary settlement. Yeah, but I'm not sure that's civil engineering consider it or not. Yeah, because compared with the primary settlement, it is a very small value. Yeah. Thank you.
When I take a look in your geologic model, you show very high subsidence rates in Midtown and downtown, and in your geologic model you show that as a fill, but in fact all of those buildings are dug down to bedrock. So they should be much stiffer. Also, do you take into account that excavation of the mass that's dug out for the basements of those buildings, to take that out, because then there's a negative weight from the excavation?
Yeah, so in our research, I think we don't consider the basement. Yeah, we only consider like for the height, and we convert it to the floor. Yeah, 4 meter convert to the floor. So I trust that we don't consider the basement. Yeah, so yeah, it is what we can do in the future. Yeah, thank you.
Klaus had a question.
Yeah, it's more comment rather than a question. First of all, my guess would be that the subsidence rate in soft sediments, whether they're clay or till or whatever they are highly time dependent. I mean, you mentioned that there's initial subsidence in the first year, but that continues to decrease over time simply because of dewatering and other effects, consolidation of the pore space and so on. So I'm not sure what kind of soil model you actually used and how much you spend in the geotechnical realm, but I have some serious questions. The other thing is many high-rise buildings in New York City that appear to be on soft soils, depending, of course, where they are located, have different types of foundation systems. One have just friction piling or a mat underneath. So that would transfer the weight of the building directly onto the soil. But many have so-called end piling. The piling goes all the way down to the solid bedrock. So even so they may have soft soils underneath of them, the weight is really transferred by the end piling to the bedrock. And so unless you really take each of those construction details and geological conditions into account, you end up with a terrible mess, okay? For instance, when Battery Park City was using the fill from the World Trade Center excavation, that Battery Park fill was sitting there for, a good fraction of a decade to naturally consolidate in part, enhanced by machinery consolidating it from above by vibration. And then they built the buildings on top of it, including friction piling, to the best of my knowledge, so they couldn't reach bedrock there. So unless you really take all that geotechnical and structural detail into account, and you have 100 by 100 foot footprint where you're mixing street level subsidence with building subsidence, boy, you have a hard time really separating out a building component alone. One other general comment. Compared to the sea level rise, it's nothing. And so, I mean, it's theoretically an interesting exercise, but from a risk assessment for New York City, sea level rise is the driver. None of these factors that, as interesting they are, to distinguish between post-glacial isostatic adjustment from 10,000 years and older into the present, from the building and construction to the geological. That's all overwritten by sea level rise in terms of policy issues that we have to consider. That's my comments.
Thank you. Yeah, I agree. Yeah, so yeah, I agree that in New York City, because sea level rise rates can compare to the subsidence we calculate. So yeah.
No, that's not the point. The subsidence, I mean, yes, there's a contribution from sea level rise to the subsidence too, but I mean, the local sea level rise. Look, by the end of the year, it's half a meter or a meter. So, I mean, those millimeter subsidences, they peter out with time, and so they are small. Anyhow,
I disagree. I think. What exactly do you mean? I mean, the rate of sea level rise in New York City, excuse me, over the last 20 years is about 3 millimeters per year, and the rate of GIA is about 1.5 millimeters per year. So that adds. I mean, the ocean and landside are almost equivalent.
That's the current rates. Go to the NPCC tables and go to 2100, and then you can choose your percentile.
Yeah, but the
They're going
VLM
up to
projections
half a
are
meter or a meter.
the VLM projections in the IPCC reports are an open area of investigation. So we really don't. They're very low for New York City, but I'm not sure they're accurate.
Well, you better discuss that, Philip Orton. Right.
It's in IPCC. They admit to it in that report. They say the VLM projections need work, but
No,
yeah.
IPCC are not applicable to local sea level rises.
Agreed,
No,
but you did just
global
say that
estimate.
those were the ones that you're basing this off of.
No, absolutely not. COP et al. And so on are the sources for the New York City area.
And for the IPCC. I think Jackie had her hand up for me, by the way. So she.
Okay.
Thanks, Frederick, and thanks, Brett. Happy to chime in on the GA. I was just gonna very quickly agree with Brett here. I mean, on the modern, historical, and near future sea level rise predictions, GA, just if you look at the rate, seems like not a negligible contribution. But let's move on. I had a question, actually. First of all, thanks so much for the presentation and summarizing those results. I was curious why in the study you decided not to calculate or comment more on the modern rates that it contributes, because it's kind of difficult. You showed the comparison towards the end of your presentation, right, in the INSAR predictions of the rates, and then the absolute magnitude of subsidence from buildings in your different scenarios. But that's of course difficult to compare, because one's the magnitude, the other one's the rate. And so I was just, and I understand calculating the rates a little bit more difficult, but I was wondering why there was not more focus on trying to tease out the actual contribution that would also get at Vivian's point in terms of figuring out what's actually the contribution to the modern rates. Does that question make sense?
You you mean that's why we create different models to different materials models?
Yeah, I guess I was wondering, your predictions are absolute amount of subsidence for different soil types. And I was wondering why there was not more effort spent on predicting modern rates of subsidence based on different soil types, because that's the quantity you could compare to observations. That's the quantity that's most relevant to us today, right? So I was just curious about that.
Yeah, so because we use different models, want to show that the different soil type is a big impact for the subsidence rates. And so in the ABC model, we use different soil type, and for the D model, we want to combine with the real situation. So we consider the geological map and create another model which is closer to the real situation. But because we know that the rock, the bedrock is very different in the New York City, so we use another model to show that if all buildings are on the bedrock, the subsidence rates will lower than 5 millimeter per year. So the main thing we want to represent is different soil type will impact a lot. But if the building built on the bedrock, the subsidence rate may be lower than built on the sediment type. So this is why we use ABCDE models and compare with the real data. But because the input is the weight of the building, so we only can get the accumulate the total subsidence caused by building from our models. We cannot calculate. Yeah, maybe we can calculate the only show the second settlements in our model. It will be more easier to compare. It is what you mean. Meaning, yeah. So this is a good good suggestion. Yeah, if we can create different models, create different representation, like separate primary settlement and secondary settlement, it will be comparable. Yeah. Thank you.
Thank you. Thanks so much.
Hi again. That was a really nice talk. Thanks for presenting this. I had a couple questions on your INSAR processing. So the first one, just two. One, hopefully the first one's quick. Why did you choose to use 5 images per year, or was it 6? I forget, but that seems arbitrary. And how did you decide that?
Okay, so because actually from Sentinel-1 we can get more than 12 image per year to process, but because I have a previous research and we found that for the 6 image per year and 12 image per year, it will not affect a lot in our results. So because of it, we choose 6 image per year, not all image per year. Yeah, because because we found that if I choose all image per year, sometimes it will include some noise in my data. I mean that when I plot the time series, it will up and down, and sometimes it is not a good things, and I prefer to choose 6 image which has clear signal, not all image. Do you know what I mean?
Yeah, I think that's kind of helpful. I mean,
just our strategy, but sometimes because that process INSAR in a big area, it is time consuming. So we found that 6 image per year or 12 image per year not affect a lot. So it is one of our strategies, since that it will not affect a lot of results. Yeah.
I think well, first of all, Sentinel passes over New York City every 12 days. So there should be substantially more than 12 per year. And the reason we do this, right, is because of atmosphere. And atmosphere is considered random and will cancel if you have enough data. So I know you are using train, but I'm not sure 30 images is enough to have a full random sampling of the atmosphere to cancel. So that might be something to consider. But I wanted to just quickly ask, get your thoughts on the anthropogenic idea that you presented at the end there. And we do have lots of anthropogenic signals in VLM. And what is your feel on we use linear trends to represent this. We always use linear trends in the INSAR and VLM community, right? But is that, how appropriate do you think that is? And do you have any thoughts on how we might improve that going forward with again, the knowledge that anthropogenic is going to be nonlinear in general?
Can you say it again?
It's a hard one. Yeah. Sorry, I know we're at the end of the hour. Basically, I'm just asking, we have anthropogenic sources. Anthropogenic sources are typically nonlinear, and we project and we look at linear rates from INSAR. Do you think in the future, how do you think we can improve upon that? Do you think we can give any just general ideas?
Because actually I focus on INSAR part, and I meet a lot of problem caused by atmospheric error, and So yeah, so because a lot of urban area which subsidence rate is not very large, like New York City is about 2 millimeter per year. So sometimes we will think that is it error or is it the real data. So actually combined with your previous question, actually I choose 6 image per year, but I run 3 different sets and get the average to hope that we can decrease the error. Yeah, so I'm still working on how to get the more accurate data from INSAR. Yeah, so I don't yeah,
Thanks.
yeah, what I think. Yeah.
Thank you.
Philip, question?
My dog might bark at any moment. She's 16 and she's about to fall off the couch. But I have earbuds so I can move and talk. I thought 1.7 millimeters per year was interesting. Is that that was a mean rate over New York City, right?
Yeah.
That's more than what we all use, in our computations, which is more like 1.2 or 1.3 when we think about past and future sea level rise. I also thought the 2.0 for the battery, did I see that right? Battery, Manhattan battery said 2.0 millimeters per year, plus or minus 0.7 millimeters per year. So maybe it's not inconsistent with what is used with the tide gauge data there, but that's important. So I'll just be with you or Brett. I think those are interesting thoughts. And then my just broader comment is it's interesting I certainly grabbed your paper the first time I heard anything about it. And I thought that I'd see more the big question for me for a long time, because I studied Jamaica Bay, part of New York City, to the southeast a lot, is do they have more subsidence there? Because I apply that Manhattan rate where it's bedrock to this area that has much deeper bedrock, and so probably some compaction. There's a lot of landfill, but your results. So that would be a valuable thing out of your work and Brett's work, would be to know what the mean land elevation changes around Jamaica in the floodplains of Jamaica Bay. If that's something that could be found, that's valuable. There's a lot of effort to mitigate flooding there. I imagine it's probably a little bit more than 1.3, and maybe it's on the high end, like 1.7. But those are all things that swirl around in my head. I don't know if you have anything there that jumps out, Pei-Chin, to talk about. But is 1.7 millimeters per year, you feel like that's a mean rate for the city? And is that based on a long enough time period that you feel like that's a good long-term estimate or not?
Yeah, I think it can represent the long term in New York recently. I trust. Yeah. Yeah.
How many years is that based on, that trend? 5 years?
5 year, 2015 to 2020. Yeah.
Yeah.
Yeah, the thing I trust my data is because it also can compare with the GNSS data near Manhattan. So I think I can believe my data. Yeah. Yeah.
I think that long-term rate is a good one. I think it's basically just GIA. If you average over the study area, it's going to be, and it falls pretty well within the different GIA models in that region. But I do think that the wetlands in Jamaica Bay will be subsiding substantially faster, like on the order of 2 or 3. But Pei-Chin, you probably saw this too. The wetlands are typically really hard for us to see, just in terms of data processing.
Well, there's people who are measuring wetland elevation change, right? Dorothy's on the line somewhere there. So it's more about the neighborhoods that I'd be interested in knowing more about.
Okay. Yeah, I'm sorry. I'm looking at my map right now of New York City.
And so the difference between
coming out soon, but
so 1.3 you said is probably correct for GIA, but 1.7 is the total average subsidence rate in New York City from the study, Pei-Chin?
Yeah, because like some of the area have like 4 millimeter per year subsidence rate locally in summer, some local areas. So maybe it is because it's contributed by some localized subsidence. So
Got it. Yeah, that's useful. Useful to know.
From my understanding, there's three GIA. If I remember correctly, I looked at 3 GIA models over in New York City, and I think one has a rate of 2 millimeters, one has a rate of like 1.1, and one has about 1.6. So it's I think that background rate is all within that range of what GIA might be.
Okay, well, we're about at the hour, so I guess maybe we can stop here. With any quick comment? Okay. So thanks again, Pei-Chin.
thank you.
Nice.
Thank you.